by number of upvotes. Our next question is Claudia. Claudia is a research team lead in Babylon Health. Babylon Health was founded in 2013 with the goal of using artificial intelligence to improve healthcare. I'm particularly interested in her talk because I used their system, and I was wondering how they are taking the input from the user and translating into a useful insight. She studied at the Technical University of Dartmouth, and she also has a PhD from the Imperial College of London. So thank you, Claudia, for being here, and I will pass the presentation to you.
Can you see my screen?
Not yet.
Of course, we tried this many times, and then the one time it doesn't work.
Yes, now it's working.
Okay, wonderful. Right, thank you very much for the invite to speak a bit about Babylon Health. I just first want to say also, I hope everyone is doing okay in the lockdown. I know it's quite a difficult time, of course. Also, I should say, I'm not sure that I'm actually going to answer everything that Leo wanted to know, but I'm happy to answer some more questions later on. So let me first tell you a little bit about Babylon Health. So the mission of Babylon Health is actually not necessarily using AI, but the mission is to put accessible and affordable healthcare in the hands of every single person on Earth. And AI can potentially be useful for that. Now, for those of you who don't know Babylon Health, Babylon is an app, and we provide various services that you can use through this app. Most people probably know the video consultations. So you can have a consultation with a GP 24/7, and you can usually get an appointment within at most a few hours. And we also work with the NHS. It's called the GP at Hand service. So you can basically talk to an NHS GP through the Babylon app. I should mention this is if you are living in London right now, but we are expanding. Then going more towards AI, we also provide a triage system called Ask Babylon, where you can enter symptoms if you're not feeling well, and the system will triage you. Another feature is that you can create a digital twin. So we'll ask you some questions about your lifestyle, about your daily activity, some also about your family history, for example, and based on that, the app will compute your risk for certain diseases. So for example, are you at high risk of developing diabetes? And if so, it will suggest ways of improving your lifestyle, for example, to reduce this risk. And then one of the newer features is Monitor, where you can basically track various things about your lifestyle as well. You can track your mood, you can track your sleep, you can connect with activity trackers such as Fitbit. And I think this is something that people found especially useful during lockdown, where many people are having difficulty sleeping, for example. So this can be a great way of figuring out why, for example, you're in a bad mood or why you're not sleeping so well. So if you haven't seen the app before, haven't used it before, I can highly recommend using it. Now, what I really want to talk about today, though, is how we deal with medical terminology. So we're using AI not just for those user-facing products, but we're also trying to use AI to improve our internal services. So for example, help our AI clinicians, sorry, not AI clinicians, help the GPs who are doing the video consultations to work more effectively. For example, by showing them things in the medical history that are useful or similar. So one of the challenges with that is that medical terminology is like you need a lot of like understanding to get it. Like I mean I'm not a doctor, and if I look, for example, at these terms that a doctor would use, I mean I know some of them, like malaria. I've even heard sinusitis just because I've had it myself. But paludism, I have no idea what that is. Whereas for a doctor, it's completely clear. Now, the problem here is that if you have a medical, an EHR, an electronic health record, where the events throughout your life, your medical events are being recorded, it can happen that, I mean, lots of these come up, lots of these medical terms. And the question though is like, how are they related? For example, I know that influenza is the flu and sinusitis, well, it's something to do with the sinuses. So they are somewhat related. They're not exactly the same, but they're related. And if I go talk to one of our doctors, the doctor will tell me that indeed paludism is a synonym for malaria. So we here have two different medical events with two different medical terms that actually mean exactly the same. And the same happens if you're looking at medical notes that the doctors write during a consultation. You have, for example, sinusitis mentioned here, and then sinus infection mentioned here. So they are exactly the same thing, but the doctor uses different things. Now, of course, if we want to use machine learning models, this can be problematic because we need to be able to represent these medical terms in such a way that it's clear for the model that these two mean exactly the same and that paludism and malaria are synonyms. So how do we do that? If we just look at the medical terms and feed them into the machine learning model, obviously that doesn't work for various reasons. First of all, the similarity between medical terms is not represented in the strings. Like paludism and malaria look completely different, even though they mean the same thing. And also, we can't just feed strings into machine learning models. So usually you need some kind of numeric representation, or even a better representation. So ideally, we want to represent the medical terminology, medical words, in a way, as a vector, and in such a way that medical words that mean something very similar are very close in the vector space, according to the cosine similarity between the vectors. So you want to end up with clusters of diseases, for example, or clusters of drugs that are very similar, they are very close in the vector space. So the question is, how do we get these vector representations? And this is a bit of background on NLP. I don't know how familiar you guys are with natural language processing, so I'll just briefly go over some techniques that are generally used for creating vectors. The naive way to create vector representations is that for our whole vocabulary, so all the words that we have, we create vector representations that have the dimensionality of our vocabulary, and we just assign 1 to one dimension and 0 to all other dimensions. And then for the next word, the second dimension will be 1, everything else will be 0, then the third dimension will be 1, and so on. Now, you can already see some problems with this, because I mean, I've got 5 words in my vocabulary, and I have 5-dimensional vectors. If I have hundreds of thousands of words in my vocabulary, which is the case even just for medical terminology, you'll have vector representations that are like 100,000 dimensional, which is just not very feasible. Another problem with this is, and I'm aware I'm here plotting 5-dimensional vectors in 3D space. Another problem is that if you have these one-hot encodings, each vector will basically be lying on one of the axes, which means that their they all have exactly the same cosine similarity. They are all not similar at all. So this type of representation doesn't give us this feature we wanted, that similar medical terms are close together in the vector space. So usually what people use, and this is in general in NLP, not just for the medical domain, is they use the word-to-vec method model for training these representations. So the idea here is one that comes from linguistics, namely that a word is, or the meaning of a word is described by its context. And that means its context in a large corpus, for example. So the word-to-vec method takes a lot of text, for example, Wikipedia, or in our case, because we're interested in medical terms, that could be clinical notes or biomedical research articles as well. And from these texts, we extract co-occurrences. So which words occur around a word of interest. So for example, influenza might occur a lot with cough in a window of maybe 5, so 5 words long in a sentence. Sinusitis might occur a lot with cough as well. Paludism might occur with travel. Malaria might also occur with travel. Now, the idea here is that, for example, paludism and malaria, they both co-occur with the same word, travel, and therefore they should have a very similar vector representation. Note that it does not mean that because these two words co-occur, they are similar. So it does not mean that paludism is similar to travel. Now, how are these word co-occurrences used by the word-to-vec model to form vector representations? It's basically a very simple neural network where we have an input and an output layer and just one hidden layer. And the input to the network is the word we're interested in, for example, influenza. And then the output that we're training it to output this is the co-occurring word, for example, cough. And these are encoded as one hot. So the input and the output layer, they'll be massive. They'll be like hundreds of thousands. The dimensionality will be like hundreds of thousands. And what we're interested in is the hidden representation here that the network learns given an input trying to predict the output. And this is usually of much lower dimensionality. Often people choose like 500, 12, 32, 300, I mean, you name it. And the idea is that if you think about these two words, influenza and sinusitis, which both co-occur with cough in the corpus, basically what your training network to do is for both of these, so two different input vectors, predict the same output. And in order to do that, it needs to encode both of these input vectors as similar hidden vectors. And that's why we at least hope, if we train the network well and our corpus is a good corpus, we hope that we get a good hidden representation, which is then our vector representation, or embedding. That's what we usually call it. So we'd hope to end up with something like this, where you now have vector representations that were learned by the neural network, and you have similar ones close together in the vector space. Like here we have malaria and paludism. Now, so far, these word-to-vec representations, they learn vectors for words. Now, what do we do in the medical terminology if we have a term that's made of various words? What's usually done is very simple. You just average the vectors of the single words in the term. So something like sinus infection, the average sinus and infection, and then you hope that it ends up close to the vectors that are similar. You hope. Whether or not that's the case, yeah. Another slightly newer or way of creating embeddings, vector representations of words is Elmo and Bert, or various other characters from the Sesame Street. And these are contextual embeddings. The idea here is that you don't just represent, you don't just have one vector for one word, but instead you have, you create a vector for a word based on the context it's in. So if you have a sentence like this, influenza, the vector for influenza might be this, and it's influenced or contextualized by these two words that occur in the sentence. If we have this sentence instead, the vector might look slightly different because now influenza, the vector for influenza, is contextualized by the other words in the sentence. So this sounds like quite a good idea for our medical terminology, because if we have multiple, if you have a medical term that's made of multiple words like sinus infection, we again would take the average of both words, average of both word vectors, but this time the vector for sinus is contextualized by the vector by infection, and the vector for infection is contextualized by sinus. So we kind of hope that we end up with a better vector representation of multi-word terms. Now, I've talked a lot about, or given you a brief introduction of how to represent or how to create these embeddings for medical terminology, but actually in terminology in general, or words in general. And now the question is, I mean, what originally what I was interested in is, can we really use these vector representations, and do they provide the same level of deep understanding that a doctor has about the medical terminology? And in particular, are the vector representations good enough so that their similarity in the vector space represents the similarity, the actual similarity of medical terms? Because this would be quite crucial for applications. So luckily, there are already some data sets out there, even in the medical domain, for testing term similarity. And usually they look like this. They have two medical terms, and then they have a similarity score, something between 1 and 5 usually, but the scale could be slightly different as well. So renal failure and kidney failure have a high similarity because kidney and renal are basically the same thing, whereas depression and cellulitis have a very low similarity score because they are very, very dissimilar. So let me show you a bit more about these data sets. Here I'm just plotting the size of the existing data sets, and you can see what size means, the number of these term pairs that are in this data set. And you can see that a lot of them, they have like, so these have like something like 30, this one has 100, these have like 300 or 500, and these have 1,000. Now, if you think about it, like even 1,000 term pairs, what's that compared to the whole medical terminology? Like, if you think about how many different medical terms there are, it's way, way more than that. So if we test our embeddings on how well they represent similarity between terms on these data sets that are not particularly large, it's unclear whether the result is really generalizable. So if one of my embeddings performs really well on these data sets, can I really, does it really tell me that it's gonna perform well on all of the medical terminology? Will it really work in a real world application? And this is what basically what we set out to, well, investigate. And because the problem is not just that these data sets are very small, it also means that they only have the most frequently occurring terms. So even if an embedding performs very well on them, it's unclear how it will perform on the less frequent terms. So what we did to start with is test the embeddings on these data sets just to see what we get. What do I mean when I say we tested the embeddings? I mean that for each term pair, we used the embedding of the first term and the embedding of the second term and measured their cosine similarity, so the vector similarity in the vector space. So you get a cosine similarity, and now you want to compare how well this cosine similarity reflects the actual similarity scores. Because the cosine similarity is on a different scale to the similarity score, so cosine similarity is between -1 and 1, where 0 means there is no similarity whatsoever between the vectors, and 1 would be a good similarity. And so in order to measure the difference or the how well these similarity scores reflect the true similarity scores that are on the different scale, we use Spearman's correlation. Excuse me. Yeah, we use Spearman's correlation. And this is what we got. I know there's a lot going on here, so bear with me while I walk you through it, because it's actually quite interesting. So I here plotted different types of embeddings that we've tested. This is actually only a subset of the ones that we investigated. So these are all biomedical word-to-vec embeddings. So they are all trained on biomedical texts such as PubMed or the medical articles in Wikipedia, for example. Then these two here, they're just the normal glove and fast text embedding that are not trained on any specific, medical texts. So also word-to-vec model, but non-medical. And these are some of the contextual embeddings where this one, Elmo, PubMed, and Cybert, they are both trained on medical text, whereas GPT was not trained on medical text. Now, what do we see here? We see various things. First of all, if we look at the scores, so these are for each of these embeddings, you can here see the Spearman correlation. So basically, how well the embedding performs on the similarity task. And the first thing we observe is they actually have quite a high Spearman's correlation. So that means they actually seem to perform quite well on these data sets, on these similarity data sets. I should also mention, so this is one data set, and this one is another one. This first data set has about 30 term pairs. This one has about 500. So it looks as if, I mean, here it's slightly lower, the performance is between 0.5 and 0.6, but still not completely bad. There is some correlation between the cosine similarity of the embeddings and the real similarity score. However, the other thing that I plotted here is, and you see that with the color red means that there is no statistical difference, significant difference, between the performance of these embeddings. So usually you're not just interested in whether one model performs, in this case, model meaning embedding, performs slightly better than the other, like does it have a performance that's 0.05 better? But also you want to know whether this difference is statistically significant. And because these data sets are so small, we do barely observe any statistical significant differences between the performance of these different embeddings. So even though some of them have slightly higher scores than others, it doesn't really tell us anything about which one will really perform better in real life. So what we set out to do then was to create our own data set. It was clear that we needed something that was much, much bigger because the existing data sets were way too small. Now, for those of you who've created data sets before, you'll know that this is generally a painful process. And in particular, in an expert domain, you often have to involve experts to create data sets. So it's very time consuming and resource consuming generally. Luckily, the medical domain actually has a lot of resources. And we had the idea to create the data set automatically, create a large-scale data set automatically. We leveraged what's called the SNOMED CT ontology. So this is a hierarchical structure containing basically all medical concepts you can come up with. It was created over years by hand by doctors. And so it really provides like really good information. In addition to providing a hierarchical structure of medical concepts, it also provides information about each of the concepts. So when I say concepts, I mean like different types of diseases, different types of drugs, things like that. And for each of those concepts, SNOMED CT provides a main name of it, and then it provides various synonyms as well. So here we have the main name being malaria, and then synonyms, for example, being paludism. Now, this is exactly what we were interested in. We wanted medical terms that are similar, or even better, here we have synonyms. So what we did is we extracted this information from the whole of SNOMED. So SNOMED has 350,000 concepts. So for each of those, we looked at all the medical, the main name and all its synonyms. We paired them and said, okay, they have a similarity score of 1 because they are synonyms. And we also did the same and paired the synonyms between them, because if paludism is a synonym of malaria and plasmodiosis is a synonym of malaria, then you can assume that the two of them are also synonyms. So this is a second slightly larger data set that we also created, where we added those additional synonym pairs as well. So this gives us like a huge amount of similar term pairs. I'll briefly skip that. We also used another part of SNOMED to create some more pairs of basically extracting them from concepts that have been replaced by other concepts in SNOMED. Now, if you look at, this is just an example from the dataset we created. And what we can observe here is that some of these term pairs that we extracted, they are like super similar, like splinter leg, splinter in leg. I mean, I can tell that they are similar. I don't need any like proper medical knowledge to tell you that these are similar. So I'd assume that for any vector representation, it should be quite simple to figure out that these are similar. On the other hand, if you look at the term pairs down here, I wouldn't be able to say that these are similar. They look completely different, and you really need a very deep medical knowledge and understanding to figure out that these are similar. So we thought, okay, this is cool. It would be great to test our embedding methods separately on the easy ones and on the hard ones, because my assumption is that the hard ones might be hard for embedding methods as well, because you really need this very deep understanding. How did we distinguish them? We used Levenshtein distance, which is the single character edit distance between terms. So for example, if you look at splinter leg and splinter in leg, to go from one term to the other, you do one substitution and then you do one insertion. So you have a distance, Levenshtein distance of 2. And you see that the Levenshtein distance of all these easy ones are quite low, and the Levenshtein distances of the difficult term pairs is quite high. So we distinguish the easy ones from the hard ones by setting a threshold of 5 and thus separating the data set into 2, an easy part and a hard part. Now, so far, we actually only have pairs of terms that are similar. But of course, we also want some terms in our data set that are not similar. And we then decided we'd actually create a binary data set rather than assigning a score between like 1 and 5 or something. We just do either it's similar or it's dissimilar. So the question is, how do we get these dissimilar pairs? Now, a very naive way of getting dissimilar term pairs is to just randomly match some of the terms in the data set. And that's one of the strategies we used. If you do that, what you'll observe is that, especially in the easy data set, that you now end up with the terms that are similar in meaning, that have a similarity score of 1. They are also lexically very similar. They look very similar. Whereas the term pairs that are dissimilar in meaning are also lexically very dissimilar. So we didn't think that this would be very good because it would probably be very easy to figure out for a term representation model that the lexically similar ones are similar and the lexically dissimilar ones are dissimilar. So we needed a better strategy for getting negative samples. And the idea we came up with is the following. We thought, let's make it really difficult. So we chose to match each term with a term in the data set that looked very similar, that had the smallest possible Levenshtein distance. So for example, polyscialia, which is excessive salivation, right? These two have the same meaning, similarity is 1. Polyscialia, we looked at other terms that have Levenshtein distance as small as possible. We found 2, Physalia and polythelia. These mean something different, I believe. So we assigned the score 0 to them. So they are dissimilar in meaning. So what we've created now is a data set that should be highly difficult unless you have a really good understanding of medical terminology. We have term pairs that look very different, but are similar in meaning. And we have term pairs that look very similar, but mean something very different. And if you were wondering, as I said, polyscialia is excessive salivation. Physalia is this weird sea creature. And polythelia means you have more than 1 nipple. More than 2 nipples, sorry. So now that we have this amazing new data set, I should point out that it's massive compared to the ones that, that are existing. So here we had at most 1,000 term pairs. Here we have over 700,000 term pairs. So much, much more than in the existing data sets. So the performance on our new data sets can really be like a benchmark for how well the whole medical terminology is represented by embeddings. And just note, this is an exponential scale. So if you plot it on a linear scale, these just vanish. We also did a manual evaluation with doctors who basically confirmed that the labels, note, the whole data set is created automatically, right? It's like automatically extracted from SNOMED CT. And we had doctors confirm that the labels assigned as similar or dissimilar is 95% accurate. So how well do our models, well do the embeddings perform on these new large-scale data sets? Again, you do the same thing as before. You use the cosine similarity between 2 terms. And now this time we can't use the Spearman correlation between the actual similarity score and the cosine similarity because now we have a binary data set. So instead what we do is we also measure rock out, but in particular here we found the optimal classification threshold, and based on that classified each cosine similarity as 0 or 1. And then we can basically just measure the accuracy between this classification and the actual similarity score. And note that we can use accuracy here because it's a balanced data set. We created the same amount of negative, of dissimilar term pairs as we have similar term pairs. Now, the interesting bit, what's the performance like? So here again, we have 2 different data sets, 2 different of our new data sets, the same embeddings that we compared for the existing data sets. And this is the easy data set. So where we have similar pairs that pairs of terms that look similar, are similar meaning. And we can see that for most embedding methods, they get a really high accuracy, like close to 80%. So these data sets seem to have term pairs that are quite easy to figure out for embeddings. However, if you look at the hard data set, remember the hard data set has term pairs where terms that look very dissimilar are similar meaning, and vice versa. So pairs that look very dissimilar are similar meaning, and those that look very similar are dissimilar meaning. So where you really need a deep understanding. And we can see that here, the best performance is like just over random, basically. So it only gets like just over 50%. So it is really a really difficult data set for those embedding methods to figure out which terms are similar and which ones are not. The other important thing that we see is that we now have significant performance differences that can be observed between the different embedding methods. Even though the accuracy scores are not hugely different, because the data set is so large, we now can observe statistical significant differences. So this enables us to really say which of the embeddings is better than the others. Now, I should probably say a little bit about what's next, because this is basically what the work we've done. If you want to know more about it, we recently published the details in the AAAI conference this year, and you can also find the code for creating the data set on GitHub. Next, of course, you know, as I showed you, the existing embeddings are just really not up to properly showing the similarity or properly identifying the similarity between medical concepts. So what we need is better medical concept or medical term representations. And there are various ideas out there that could be useful, like some people try to include knowledge, for example, from an ontology like SNOME-XLT or from other resources into the embeddings, or map embeddings from one embedding space into another more interpretable one. So there is like lots of scope out there for creating new embeddings. The cool thing is that now with this new data set, we basically have a new benchmark to test any embeddings anyone comes up with. So if you have any ideas, let me know and I'll be happy to collaborate on something. Yeah, and with that, thank you very much for listening, and I'm happy to answer questions. And I think there are already some. Maybe I'll go through the questions on the talk first. Leo, what do you think? Yeah, go for it. Do you want me to read it? I've got it in front of me, so okay. I can. Well. Go for it. So, do you use the term representations in production at the moment? If so, how do you apply it? Right. So, I mean, we use some kind of term representations in some production, yes. However, I mean, the thing that I didn't say here is, I mean, I kind of trash talk the existing embeddings, I have to admit. However, what I didn't say is, if you have embeddings that don't represent terminology that well, it doesn't necessarily mean that they don't perform well for your downstream tasks. Especially if your downstream task is focused on nearly always identifying the like very common medical terms. It could be that even if you have a mediocre representation of medical terminology, most of your use cases are actually covered or will perform well. So we are using some, but although not in many applications. Right, let's see. Then there is, Word2Vec is quite a costly algorithm computationally. how does it impact model runtime? If a lot, how did you solve this? Right, so in this work, we didn't actually train word-to-vec methods ourselves. What we did is we looked at all the existing metrics, sorry, not metrics, all the existing embeddings out there. So the ones that you can find open source, basically, because we thought rather than going out and training yet another word-to-vec embedding ourselves, let's go and look at and evaluate the ones that are already out there. Right, then we've got, wow, oh, did I skip one? Could you expand on how you assess statistical significance? Yeah, that's a really interesting one. So what we did is we used two different types of statistical significance. And I have to admit, I have to look at the details myself right now, because this is a while ago that we did this. I'm sorry, I would refer to the paper because we have the details there. I can't remember exactly what we used right now, so I'll just go on to the next question if that's all right. How I should have, Leo, are you marking them as answered?
Yes,
oh, okay.
I meant the other two, yes.
Okay, so how do you manage correlation of terms by chance when performing word co-occurrence in the corpus? So if this is about the training the word-to-vec model, I mean, usually you use like massive corpora. I mean, if you imagine the whole of Wikipedia, yeah, I guess some terms will occur by chance. If something just co-occurs like once, you won't really consider it in your training. So it's only things that co-occur together quite often. So that, yeah, I mean, it really works very well. And I guess because it's a neural network, the word-to-vec method, I mean, neural networks are quite good in figuring out kind of outliers and like filtering out noise. So it's really not a problem. Then you said you have real similarities between the words. How did you come up with this? Have you labeled them manually? Yes, very good question. So in the existing data sets, they were all created manually by doctors. So doctors were given, or medical students were given 2 term pairs, and they had to assign a similarity score between 1 and 5. In our case, the whole, I mean, the data set is like super big. It has like 700,000 term pairs, and in that case, they were all created automatically. So we automatically assigned the score similar 1 or dissimilar 0 to them. But we did do a manual evaluation where we basically gave a small subset of term pairs that was randomly selected to doctors and asked them to assign a score of either 0 or 1. And we measured the accuracy of that, and it showed that the accuracy when taking the doctor's evaluation as ground truth was 95%. So the labels are mostly correct in the data set. And again, even if some of them are not, the data set is so big that it doesn't really matter. How does the co-occurrence of comorbidities affect their embeddings? Does, for example, heart disease have a similar embedding to obesity? Yeah, this is a super interesting question, actually. Thanks for asking that. Because you're mentioning something really important here. So I've only talked about similarity in the sense of kind of synonyms. And if that's what you're interested in, then the data set we've created is really useful. Another thing, though, in medicine that can be important is how related two concepts are. And related can be, as you say, regarding comorbidities, or, for example, cause-effect relationships. It could also be like just how related things are, like how useful is knowing one thing for the doctor to diagnose the patient, and it's unclear whether embeddings are very good for that. I mean, the existing data sets, they kind of, I mean, some of them are meant to have scores for similarity and some of them for relatedness, but really I have to say I'm not convinced that there is much difference between these data sets. I think they all really do similarity more than anything. But it's very difficult to distinguish relatedness from similarity. So yeah, it's a really interesting topic, and I assume if you really want something that represents relatedness of comorbidities, then you probably want to train your embeddings in a different way, and not necessarily just using the normal word-to-vec algorithm. Right, shall I answer the last question as well? It was about Ask Babylon. How does Ask Babylon compare to the current NHS website service? Does it also give recommendations about whether to see a doctor, or does it give likelihood of what's wrong? Right, yeah, so it also, I should mention, it also currently has advice on COVID-19. So if you have symptoms, you can also use Babylon to triage that. I have to admit, I don't know what the current NHS website service looks like, so I'm not sure what exactly they provide there. So it depends on what kind of symptoms you enter, whether the system just says you should go straight to A&E, or whether it in some cases it also gives you likelihoods of different diseases. So I hope that answers the question.
Great, thank you, Claudia, so much. Thank you also for the interesting answers. So that's it for the meetup for today. Again, this is recorded and will be made available for all attendees soon. Kelly will send a message, probably maybe not Friday, but on Monday. So you will receive also the recording from Claudia's talk. And thanks again very much for all participants, in particular Kelly, Laura, and Claudia. And hopefully I will see you for the next meetup. Bye-bye.
Thank you.